With an NMOS, you have a p-type substrate that you then create two heavily doped n-type regions. These two regions are called the source and the drain region. With our knowledge of semiconductors, you can see that you're creating a p-n junction between the substrate in these two regions. On top of the substrate, an oxide, which acts as an insulator, is deposited. Then on top of that, a layer of metal is deposited, which finalizes the gate structure. Now you can see where the metal oxide semiconductor in MOSFET comes from. But it may seem strange to have your gate being completely electrically isolated from the rest of the circuit. This is where the FET term comes in. Even though there isn't a direct electrical connection, the voltage on the gate creates a field effect. As we know from our studies about diodes, at a p-n junction, a depletion region is naturally created even when there are no electric fields. This is the natural state when the gate voltage is 0 and the MOSFET is operating in the cutoff region. This is an operating region, not a physical region, which can be confusing. If you increase the gate voltage, that positive voltage will repel holes in the substrate away from the area between the source and drain, an area called the channel region, this time a physical region. As the free holes leave the channel, only negative fixed ions are left, creating a depletion region across the entire channel. Besides this depletion region, an inversion layer of electrons starts to form at the source, and as the voltage increases, that inversion layer expands toward the drain. However, at this point, when the gate threshold is not yet equal to the threshold voltage, free carriers do not yet connect all the way from the source to the drain. This area of operation is called the saturation or pinch-off region. However, as the gate voltage continues to increase, increasing the electric field, and finally passes the threshold voltage, electrons from the source and drain flow in and form an inversion layer of electrons that connects the source and drain regions. Now that they're connected, if a voltage is applied across the source and drain, a current will flow. The MOSFET is now operating in a linear or triode region. This is how, using a metal oxide semiconductor structure, you can use the field effect of a gate voltage to create a semiconductor switch. And to get a PMOS device, you have an N-type substrate and heavily p-doped wells for your source and drain. And the current carriers are holes instead of electrons.